Part C, Sue constructs a new circuit where she uses a 6-ohm resistor connected in series with a coil and an ideal AC ammeter. They're all connected in series to the same 12 volt 50 hertz AC supply. Sue measures the RMS current to be 0.657 amps. Show that Sue needs to use the results from both circuits to determine the true value of the inductance of the coil, or determine that the true value of the inductance of the coil is 40.2 millihenries. So I think this is getting at the issue here, that this inductor actually has a little bit of resistance to it, and therefore the true inductance is not quite the same as the one measured using that equation. Okay, now how are we going to do this? That diagram I think is going to be rather helpful. So let's change our circuit. What have we got now? So we've got our 50 hertz and 12 volts. We've got a 6-ohm resistor. Here's our L, which of course in reality has a bit of resistance in there as well. And our ammeter records 0.657 amps. And what we want to know is what L is. So how would we go about doing that? Now, on the face of it, we know everything except L. We know the frequency, we know the voltage, we know that resistance, we know the current. The only thing we don't know is L, so surely we can do the problem. But I think the issue is that we've got a little unknown resistor. We'll call it small r, hiding in there. And let's see on the phase diagram how that's going to work out. So our voltage over the inductor is going to go like that. Now we have two voltages over, we have two resistors. We've got a V, we'll call this capital R, 6 ohms. We've got V over R, and we've got to add to that a V over that little R there. If we add them together, that is our V total. And we know V total has got to be 12.0 volts. We also know that I total, or the current, 0.657 amps. Okay, well, some of these things we can work through. We know VR because we're given R, so that is 6 ohms times 0.657 amps. So we know that one. This we don't know because we don't know our little resistance R. What is that one? I think that's where we've got to go from our previous question to put in that. We also know, because that V total is 12 volts is going to be equal to VR big R plus small r squared plus VL squared square rooted. So we have an unknown there. We have if we pull that one in from previous question, and how then do we get I'm a bit stuck on this one. So what am I trying to find? I'm trying to find L. So I'm trying to find what the voltage is. Let's make this a bit simpler and see whether maybe I'm overcomplicating this. Let's get rid of that. Right. And let's just do the case where you've got that and that. So our phasor diagram, we've got a voltage over L, we've got a voltage R, and there's our net voltage VL squared plus VR squared equals 12 volts squared by Pythagoras. Now, what do we know? Well, we know that VR, because it's just a resistor, is I times R, so it's 0.657 amps times 6 ohms, so we know a value for VR. VL is going to be 1 over omega L. Omega we know, L we want to find, that's our unknown. So if we know VL, we can get there. We don't know VL, but we do know that VL squared plus VR squared equals 12 volts squared, and we know VR, that'll tell us VL. So, L equals the square root of 12.0 volts all squared minus VR squared, so that's 0.657 amps times 6 ohms all squared. So VL equals that, and then L equals 1 over omega times VL, 1 over 2 pi f. Right. Now, 1 over omega L is VL over I. So VL is I, which we know that one, so it's I over that. So 1 over, so I 0.657 amps over omega times, so 2 pi f times VL. And that will work. except we haven't needed to pull in the previous question. Now I think we're going to have to put this small r back in to do that one. Maybe I should come back to that.